Let's now apply the transmission line parameters to a problem involving coaxial cable. And what we want to do is determine the characteristic impedance of a coax cable made of copper and polyethylene, assuming that the frequency of the signal being applied to that transmission line is 1 gigahertz. And the geometry of the coax cable is as you see here. So the first thing that we need to do is just check to make sure that the distributed parameters are valid. So what we want to do is we want to check the skin depth, and the formula I gave for you for skin depth is 1 divided by the square root of pi frequency magnetic permeability of the center conductor times the conductivity of the center conductor. So frequency was given to us as 1 gigahertz. The magnetic permeability, we have to figure out what that is. If we look at it, we see that the center conductor is made of copper. So what we're looking for is the relative permeability of copper. From the table that I provided to you, it's 0.99991. It's almost 1, not quite. And then the next thing we have to know is what is the conductivity of the copper. And that same table that I provided to you gives you values of conductivity, and it's 5.8 times 10 to the 7th mhos per meter. And so if you're using the textbook, those both can be found in Appendix E. So we can now determine skin depth. That's equal to 1 over the square root of pi times 1 gigahertz. That's 1 times 10 to the 9th. Mu is going to be 4 pi times 10 to the minus 7 times 0.9991. Make sure I got them all. Nope. So that's mu vacuum magnetic permeability times relative magnetic permeability. And then finally we need to multiply by 5.8 times 10 to the 7th. All this is under the square root. And that gives us a calculation for the skin depth of 2 microns. We see that the inner conductor is 0.9 millimeters. And by the way, 2 microns is 2 times 10 to the minus 6. 0.9 millimeters is 0.9 times 10 to the minus 3. So 0.9 times 10 to the minus 3 is much, much less than 2 times 10 to the minus 6. So we can use the distributed parameters. The first calculation we'll do when calculating the distributed parameters is R prime. And this is coax. So from the last slide, you'll choose the equation 1 over 2 pi times the quantity 1 over A, where A is the radius of the inner conductor, plus 1 over B, where B is the radius of the inner side of the outer conductor. And we multiply that by pi times the frequency of operation times the magnetic permeability of the center conductor divided by the conductivity of the center conductor. So we have all these numbers. It's 1 over 2 pi times 1 over 0.9 millimeters divided by 2. I was given a diameter here. I need to convert that to a radius. Plus 1 over, we want to use the inner diameter. That's 2.94 millimeters div 2. We now multiply that by the square root of pi times a gigahertz times 4 pi times 10 to the minus 7th times 0.99991. In the denominator of that, we just put 5.8 times 10 to the 7th, and that gives us a result of R prime is equal to 3.8 ohms per meter. We'll now move on to the distributed inductance, L prime. That is equal to the magnetic permeability of the conductor divided by 2 pi times the natural log of the ratio of the inner diameter or inner radius of the outer conductor divided by the radius of the inner conductor. And mu is, again, 4 pi. Oop, I left a pi off right there. Sorry. 4 pi times 10 to the minus 7th times 0.99991. Divide that by 2 pi. And then multiply this whole quantity by the natural log of 2.94 divided by 0.9. I can use diameters or radiuses in there because it's a division operator, so just save myself a little time. L prime is, the calculation there is 240 nanohenries per meter. We'll move on to the distributed conductance. G prime for coax is given by 2 pi times sigma sub d. In this case, that is the conductivity of the dielectric material, ln of b over a, divided by the ln of b over a. So I don't know this yet. If I go to the handout that was given, I'm going to look up the conductivity of polyethylene, that's the conductor. And if I were to do that, I would find out that the conductivity of polyethylene is 1 times 10 to the minus 15th moles per meter. And I need to divide this by the natural log of 2.94 divided by 0.9. And this term dominates, and so this is practically 0. Moles per meter. Next, what we want to calculate is the distributed capacitance, C prime. And for a coaxial cable, it's 2 pi times epsilon divided by the ln of B divided by A. That's going to be 2 pi times 8.854 times 10 to the minus 12 farads per meter. That's the vacuum electric permittivity. We now need to multiply by the relative electric permittivity of polyethylene. You'll also find that in the appendix that I gave to you. Turns out that it is 2.26 for polyethylene. And again, we just divide by the natural log of 2.94 divided by 0.9. And this gives us a value of 110 picofarads per meter. So now we've got our distributed parameters, 3.8 ohms per meter, 240 nanohenries per meter, 0 moles per meter, and 110 picofarads per meter. Z0, the characteristic impedance of the transmission line, since all of these values are relatively significant, this is a lossy transmission line. We get R prime plus J omega L prime over G prime plus J omega C prime. And so now it's just a little bit of plug and chug. This is going to be 3.8 plus J. Omega is 2 pi f, so that's 2 pi times the frequency, which was 1 gigahertz. And then L prime was 240 nanohenries. So that's the numerator. And then the denominator is going to be 0 plus J. Again, we need to convert from frequency to angular frequency, so 2 pi times 1 e to the 9th. And then we need to multiply that by 110 pico. So that's the calculation for Z0. Throw this into your handy dandy fancy calculator and you get the value 47 minus J 0.06. So what we notice here is that, oh, and this is ohms, it's a impedance. So what we notice is that for a lossy transmission line, Z0 is a complex number. It's got a real and imaginary portion. So we call those complex numbers. So interestingly, a lossy T line has a complex characteristic impedance. for our lossless T-line model, we had L, the square root of L over C. Well, there's no J omega in terms of here, so that's going to give us some value R plus 0x. So interestingly, we'll always end up with a real valued number when we have a lossless T-line, which is an interesting observation. Finally, I just want to throw one more calculation in here, and that is, well, can we calculate the speed at which the electromagnetic wave is traveling through this conductor? And there's two ways we can do that. The first is if we use the material properties. Mu sub p is equal to 1 over the square root of the magnetic permeability times the electric permittivity, and that's going to be 1 divided by 4 pi times 10 to the minus 7th times 0.99991. So that's mu 0 times mu r. We then want to multiply that by 8.854 times 10 to the minus 12th times 2.26, which is just epsilon 0 times the relative permittivity. Then we need to take all that to the square root. And so that gives us a propagation velocity of this wave and that of an electromagnetic wave in that conductor based on material properties only at 1.94 times 10 to the 8th meters per second. So a little bit slower than the speed of light, which is 3 times 10 to the 8th, about 2/3 the speed of light. The other way we know how to calculate propagation velocity is based on the distributed parameter model, 1 over the square root of L times C. If we were to do that, it would be 1 over the square root of 240 nanohenries times 110 picofarads. And that's actually going to give you the exact same answer. So it doesn't matter which way we do the calculation.